Welcome back. Today we're going to talk about two little pieces of section 2.4 that kind of tie everything together and give us an idea of what are we actually doing? Why are we doing synthetic division? Why are we doing polynomial division? Why does the rational zeros test work? So we've actually, we've done those other pieces, but this is kind of what information can be gleaned from there. Remainder theorem says this. If f of x is divided by x minus k, so some linear factor, the remainder is r equals f of k. Okay, so the remainder is f of k. Okay, so we're going to be finding the remainder of a couple of functions here. And so let us see what happens. Okay, so I've got this right here, my f of x, which is 3x squared plus 7x minus 20. And what I'm going to do is I've got this right here, so I'm going to divide. I'm going to pick synthetic division. It's 3, 7 minus 20. And we're going to see what happens here when I divide it by x minus 2. So that goes here. Bring down my 3. 2 times 3 is 6. When I add, I get 13. When I do 2 times 13, I get 26. When I add, I get 6. So it seems that my remainder is equal to 6. Okay? Well, what the remainder theorem says is that my remainder is equal to f of k. So I'm going to test that theory. F of 6. Sorry, k is 2. So f of 2, and I'm going to put that back in. So 3 times 2 squared plus 7x minus 20 gives me, and this would be 7 times 2. That would be 12, because it's 4 times 3 plus 14 minus 20 is equal to 26 minus 20 is equal to 6. Well, check that out. I actually divided it and got a remainder of 6. I did f of k. So f of k is equal to 6. They match, which means my remainder theorem actually does what it says it's supposed to do. And so because of that, so we're going to find the remainder when 3x squared plus 7x minus 20 is divided by x plus 1. We need to establish what k is. In this case, it's what's being subtracted, so k is equal to negative 1. In order to do this, we're going to use synthetic division. And I'm going to transfer over my coefficients, so 3, 7, negative 20. Bring down my 3, multiply, add, multiply, and add. Well, what we see is our remainder is negative 24. What that tells us is that k equals negative 1 is not a factor. It's not a factor because if it was a factor, there would be no remainder when I divide it using synthetic division or regular polynomial division. So let's use that remainder theorem to see if my synthetic division actually works. We checked it on the previous example, so let's check it here. So I'm going to do f of negative 1 and see what I get when I plug it in. So f of negative 1 is going to be 3 times negative 1 squared plus 7 times negative 1 minus 20. I'm squeezing it in. Okay. So this would be 3 plus negative 7 plus a negative 20, or minus 20, which is going to give me negative 4 plus negative 20, which is equal to negative 24. Again, remainder theorem actually works. So now that we've seen that remainder theorem works in the previous two examples, I'd like for you to go ahead and try this x plus 4, figure out what your k is equal to, and then check back in for the answer. All right, so when k is plus 4, let's see what we've got here. So what we've got with x plus 4 as a factor is k is equal to negative 4. When I do my synthetic division here, and again, you don't have to do this once we've established that the remainder theorem works, just showing you some extra examples of synthetic division and how it ties together. So if I bring down my 3, I've got negative 12 here, negative 4 times 3. When I add 7 minus 12, I get minus 5. Negative 4 times negative 5 would be positive 20. And when I add, I get 0. Again, f of negative 4 is going to give me 3 times negative 4 squared plus 7 times negative 4 minus 20. Well, when we look at this, what have we got? We have 3 times 16 plus negative 28 minus 20. 3 times 16 would be 48 minus 28 minus 20 would give me 48 minus 28 is 20, minus 20 would be equal to 0. So again, that remainder theorem works. Check it with synthetic division. The factor theorem says this. The factor theorem says a polynomial function f of x has a factor x minus k if and only if f of k equals 0, which means this. Okay, so f of k equals 0. Using what we just talked about, this would mean that f of x divided by x minus k has a remainder of 0. So it has a remainder of 0. Well, what we're going to see is those x's at those values give us 0 when we put them into the function. Well, those are going to be the zeros of the function on the graph. So let's see. Use the factor theorem to determine whether the first polynomial is a factor of the second one. Remember, the factor theorem says that if it's a factor, then f of k is equal to 0. So I'm going to put is f of positive 1, because that would mean k is a positive 1. Is it equal to, and I'm going to put a question mark here because is it equal to 0? So let me plug it in. F of 1 is going to equal 1 cubed minus 1 squared plus 1 minus 1. Well, this would be 1 minus 1, which is 0, plus 1 minus 1 would be equal to 0. So that means that, yes, x minus 1 is a factor. When we're tying concepts together, though, let me show you how this works out. I'm going to use synthetic division to divide my polynomial by my factor k. And so when I'm using synthetic division to divide this polynomial, I'll bring down my 1, multiply, get 0, multiply and add, multiply and add. I see a remainder of 0. So this tells me x minus 1 is a factor. Where we're going with this is to say that once I find a factor and I use synthetic division, I now have that polynomial product that I have been talking about in these previous videos, and it's going to allow me to factor these polynomials. So I'm just going to give you a little sneak peek here. We're going to do a factorization of f of x. And it's going to look a lot like those polynomial forms that we've used. And so f of x is actually equal to x minus 1 times, and then I'm going to take this right here. Check it out. When I divide it by x minus 1, that's right here, my polynomial that results gives me my other factor. And so I'm going to take this. My original was x cubed, so this is x squared. This is x. This is my constant. So I'm going to have x squared plus 1. That is a factorization of my f of x. Eventually what we're going to do with that is we're going to see if we can break it down further, this one we could, to find all of the factors. Okay? So look for that coming up in videos. I want you to do the second one and take it to the point of your factorization. Check to see if the first polynomial is a factor of the second one, and then see how far you can get with this factorization. All right, we're back. So basically what we're doing is we're using the factor theorem to determine whether the first polynomial is a factor of the second one. I'm going to do it in two ways. The first one, I'm going to determine k is equal to minus 2. If it's a factor, then that means it's a 0. So I'm going to do f of negative 2 to see if it's a factor, to see if it's going to give me 0. 4 times negative 2 cubed plus 9 negative 2 squared minus 3 times negative 2 minus 10. Kind of a beast. Here we go. Negative 2 cubed would be negative 8, because 2 cubed is 8, and we've got an odd number of factors. So I'm going to have negative 32 here, plus 36, plus 6 minus 10. So here we go. 32 plus 36 would be 4, plus 6 minus 10. So that's going to be 0. All right, so what that means is x plus 2 is a factor, and negative 2 is a 0 of my original function. See how cool that is? Now we could go to our calculator, we could check it, we could see, hey, is negative 2 actually a 0? Our math would say yes, so I could check my answer. Then when I go back and I'm going to do the rational zeros test, I can say, okay, am I actually right here? When I look at my rational zeros, I look at my graph, everything ties together. This polynomial division, evaluating the factor, looking at the graph, being able to factor the whole expression, everything kind of plays together in good harmony, okay? So thanks for watching, guys, and we'll see you next time.